Okay, so now we are continuing our review of networking concepts, and specifically our review of the network layer. And the next thing we're going to focus on is we're going to take a look at the different routing protocols. So like I said, I'm assuming from our class in 475 you're familiar with the routing algorithms that are behind the popular routing protocols. So we're going to focus just on the routing protocols. So there are two different families of routing protocols used by routers: interior and exterior routing protocols. Interior routing protocols are used for passing routing information among routers internal to an autonomous system. Now, if you remember, an autonomous system is basically a system, say, like within an organization. Um, these are also known as IGP, or interior gateway protocols. Examples of these would be things like RIP or OSPF. Then you have exterior router protocols used for passing routing information amongst routers between autonomous systems, and these are obviously called EGPs, for exterior gateway protocols. So intra-autonomous system routing is also known as interior gateway protocols, the most common being RIP, OSPF, and also Cisco uses one called IGRP, which is Cisco proprietary. So we're going to take a look first at RIP. So RIP uses a distance vector algorithm, and if you've forgotten what that is, you can take a look at the notes. We have an additional material and kind of review that. And within RIP, each router computes new distances, and it basically replaces entries with new lower hop counts. So now instead of cost, we basically have hop count. So looking for the best way to get there with the lowest amount of hops. RIP inserts new entries and replaces entries with the same hop count but with a higher cost. And so we can address the issue of the dynamics of our changing networks. Each entry is aged, and entries get removed that have aged out, so we don't have invalid routing information inside of our router. And basically, the distance metric, like I mentioned before, is a number of hops with a maximum of 15, and each link has a cost of 1. And distance vectors are exchanged with neighbors every 30 seconds in a response message. This is called an advertisement. In each advertisement, there is a list of up to 25 destination subnets. So here we have a little example of a little network with 4 different routers that are attached to well, these aren't listed, but as far as external subnets, there's 1, 2, 3, 4, 5, 6. And basically what you see from the perspective of router A, subnet U is connected directly, so it's only 1 hop. Subnet V, I have to go through another router, so that's 2 hops. And you can see, etc., that each of the other subnets in this drawing are either 2 or 3 hops away relative to router A, because you either have to go through 1 or sometimes 2 routers to get to a subnet. So here we have an example of the RIP protocol in action. So in this example, we're looking at things in the perspective of router D. Okay, so and basically in this network we have multiple subnets. The ones we're concerned about are W, X, Y, and Z. And basically, we know that destination W, basically the way this is set up, can be reached. And I guess in this example, C and D are not connected to each other. But W's next hop router is A, and there are 2 hops to the destination because you have to go through your initial router plus the second router, so that's your 2 hops. Y, you have to go through B, it's the same story. And Z, you have to go through B, and the assumption is there's multiple networks because you have this thing, and basically there's 7 hops to eventually get to network Z. And X is directly connected, so it's only 1 hop. So that's pretty simplified example. So now we have the situation where we get some information. So there's an advertisement from router A to D, that router C can get to Z in 4 hops. So now once it receives this advertisement, it updates the routing table, and it says, instead of saying go through router B, which takes 7 hops, we're going to say now go through router A, which you can do in 5 hops, and of course D would not have known that had it not received that advertisement from router A. And this happens again and again, every 30 seconds or so, again, these updates. And this information keeps on changing and keeps on getting better unless something, some router dies, then it might data might start getting worse. So let's talk about that. Let's talk a little bit about what happens if a link is failed. So basically, if no advertisement is heard after 180 seconds, it's automatically assumed that that link is dead. So that kind of tells you that, in general, routers have to have a relatively quick restart time. But that 180 seconds has been kind of analyzed to death, and so that's a good standard as far as that goes. So now the routes, once we realize that that route neighbor or link is dead, the routes via the neighbor are validated. New advertisements get sent to the neighbors to say, hey, don't go there. And neighbors in turn will send out new advertisements. So the link failure propagates to the entire network, and hopefully some alternate routes around that link will get propagated as well. And what we want to do is we want to prevent any network looping in our in RIP, or in our learning about the network topology. So we have a limit of 16 hops to prevent that from happening.